Go ahead.
Okay, so good afternoon, everyone, and welcome to the first seminar of the Fall 2023 seminar series. Today we have Katrina uh, Kyprioti with us. Apologies if I mispronounced it. So this is our GSC leadership team for the year 2023-2024. We have our co-chairs, Roshan and Rachel, and then we have our publicity team, Andrew and Avinash. Uh, we have our publicity team, Andrew and Avinash, and they are the ones who send you the emails regarding all our GSC events. Then we have our huge support team. The support team has been growing a lot for the last 2 years. We have Anirban, Swapnil, Mayank, Mohammad, Latif, Filani, Nurayan, Suraj, Siavash and Louise. Siavash and Louise have just joined us this year, and I would like to welcome them to our team as well. And then we have our faculty mentor, Farooq. He has been of great help to us. So GSC has regular meetings on Wednesdays, 5:15 p.m. This happens every week, and if anyone here is interested to join our GSC meetings, they can contact Rachel or Roshan using the email IDs provided, and they will be sent the Zoom link for our meetings. Uh, Become a member of the GCOE GSC member on Engage. So we have the QR code here. So if you can scan the QR code, uh, you will be directed to the Engage page of the GSC page, and then you can log in with your OU ID and become a member on Engage. This will help us send you the emails regarding all our further events as well. So I'll just give a quick 10 seconds for anyone who wants to scan the QR code. Okay, so we also have a LinkedIn page. You can scan the QR code, which is shown here. This LinkedIn page will be a great tool to connect with all the OU alumni members, and you can connect with them, and it would be a good opportunity to talk with them on LinkedIn if you have any questions for them. So please scan the QR code, and you will be directed to the GCOA GSC LinkedIn page. We also have a Facebook page. You can scan the QR code here. All our updates about the events we do, uh, or the events which we are participating along with some other organizations, all the details will be given on the Facebook page. You can scan this QR code and join us on our Facebook page as well. We have a YouTube page. This YouTube page is basically used to upload all our previous webinars, which have been conducted until the end of last semester, that is spring 2023. If even in future, if anyone misses a seminar, a webinar, and would like to view it again at a later time, you can log into this YouTube page, and you will find all our webinars on that page. So you can scan this YouTube page. You can scan this QR code for the YouTube page and uh, watch all our previous webinars. So the GCOE GSC has a team room which is called the Dave and Susan Bird Team Room. It has the amenities like couches, whiteboards, coffee pots, microwave. You can email us if you would like to have an access to this room. Uh, you can email either Roshan, Rachel, or also Farooq if you want access to this. Make sure you include your OU ID in the email so that it's easier for us to give you the access for this room. Uh, just a quick reminder. So in a few time, the in the chat section of the Zoom, we will upload a link which is a sign-in sheet for the webinars. So make sure you sign into that and fill out the form so that we can have we can have a note of all the people attending our events, and that will help us in future as well. So today we have Katrina Kyprioti with us. Her title for the presentation is Aleatoric Uncertainty in Engineering Applications. She is an assistant professor at the School of Civil Engineering and Environmental Science. Just to give a quick background.
Going. Hey, Dr. P.
Just to give a quick, sorry, can everyone else please mute their mics, please? So just to give a quick background, so Katrina has done her bachelor's degree in civil engineering with a minor in civil infrastructure, and her master's in 2014 and 2016 respectively. She did her PhD in 2022 and is now an assistant professor at the School of Civil Engineering and Environmental Science at the University of Oklahoma. So without any further delay, I request her to share her work with us.
Great, thank you so much for the introduction. Let me share my screen. And I would like to say I'm honored. I hope you can see my good screen and you see the full screen, not one with the preview, right? Okay, great. So I'm honored that I'm giving this lecture actually to my home institution and actually to a graduate audience, since I'm not far away from the time I was a graduate student on my own. So I do feel how important these lectures are for you to kind of see outside what's out there and kind of think on the broader picture of how maybe problems that I'm solving and maybe are more related to civil engineer can have a broader applicability to what might be of interest to your discipline or your research. So the title is a little bit more focused now, and it's with respect to seismic vulnerability assessment and how we can use surrogate models to tackle aleatoric uncertainty. And in that seismic vulnerability assessment, we're actually going to use stochastic ground motion models, and we will discuss a little bit about what they are. So this is the outline of the presentation I'll give you today. I'll try to keep it short and sweet so we can discuss further implications or any questions that might arise. And I will start directly with my motivation. So as you already know, urbanization is one of the greatest challenges that we're currently facing, since more and more people are concentrating in large cities that in many cases grow uncontrollably. So this tendency is actually increasing the exposure of humans and their assets to natural disasters. And just to give you an idea, only in 2021, we had a variety of disasters across the globe. And here I'm focusing mostly on the earthquakes, since we're going to discuss the seismic vulnerability assessment and how the surrogate models are helping and chiming into it. And just to give you a preview of how 2023 will look like, right now the cost that we're facing, even just by looking at only half of the year of 2023, is 43 billion of damage caused by natural disasters. So these all events are stressing the necessity for us to take proactive measures and at the same time offer well-informed emergency response management solutions when it comes to an ongoing hazard and how people could manage such situations. So, but in order to be able, to offer realistic solutions, we need to understand that these exposures of humans and infrastructure to natural disasters is directly related to the notions of uncertainty and therefore risk. And just to give you a brief overview of different uncertainties that you can encounter, you can have uncertainty that's coming with respect to the hazard itself. So for example, how a hurricane might evolve. You can have more long-term uncertainties that also involve non-stationary phenomena like sea level rise. And then you can have what we're going to focus mostly in this presentation, with excitation uncertainties when it comes to earthquakes and structural uncertainties when it comes to how the structure is formulated. So how can we estimate risk? What's the best way that we can estimate risk? In order to do that estimation, we require to have some type of model that will be able to capture the complexity of the natural hazard, so the induced load that we're trying to have, and describe also the physical structure itself. There are many interdependencies in such models that actually create large complexity. And when we're going to discuss complexity here, we're going to be discussing in terms of how intense that computational cost is with respect to just running a single execution of that model. So think about time that you might need, but also think about resources such as memory requirements, processors, and a bunch of other associated things. So just to put it on the framework of how that vulnerability assessment is performed, on your left side, you can see that we have the uncertainties that kind of characterize our system, and that system can be anything that might be of interest to us. In this case, it's going to be characterizing the hazard and the infrastructure we're looking at. And based on those uncertainties, we will run our high fidelity, what we will be calling as high fidelity numerical model, to get back some results with respect to its response. And that might be a variety of different quantities of interest depending on what you're looking at. So this is the framework that we need to go through, but this middle part of that execution of the numerical model is the one that's the most computationally expensive. So in the vulnerability assessment, we need to actually run through this flowchart multiple times. So we need to have that uncertainty well mapped and investigate a bunch of different scenarios by running all those high fidelity numerical simulations. What that creates, it creates a big bottleneck when it comes to the computational resources that we need. So in this presentation, what I'm going to try to answer is how we can integrate those high fidelity, faithful numerical models that are quite expensive when it comes to computational resources into uncertainty quantification without increasing significantly the computational burden. And how we're going to achieve this is by introducing what we call surrogate models or meta models. So these models, what pretty much are doing is a fancy word for data-driven models. They build an approximation, a mathematical approximation of the input that describes our uncertainty to the output, which describes the quantity of interest that we're looking at. And they can do that if they're being trained properly, very efficiently, so very fast, and very accurately by imitating the accuracy that the numerical model itself should have if we were running through the flowchart that I showed on my previous slide faithfully. And I will jump directly to the seismic risk assessment and give you a brief overview also of what stochastic ground motion models are. So stochastic ground motion models are models that require as input a seismic hazard description, so some parameters and ground motion features, and also require a white noise sequence that through a filtering process will provide us with an earthquake excitation. And if we actually change just the white noise sequence without messing with any of the seismic hazard descriptions that we have provided, a different earthquake excitation will be provided by the stochastic ground motion model. So that's what we call in earthquake engineering ground motion to ground motion variability. So having built a group of earthquake excitations, and why do we want to do that? We want to investigate multiple earthquake scenarios and then induce those multiple earthquake scenarios to our structure that has its own uncertain structural parameters, run our finite element model, and record what we call the engineering demand parameter, or EDP, so record the response that might be of interest to us. And in civil engineering, that could be the peak interstory drift or peak absolute acceleration. So then we get a bunch of different realizations of this pretty much model by just having one earthquake excitation going through the structural uncertain parameters to be mapped around the response that we want to record. And actually, when this framework is used in the context of seismic risk assessment, two main causes of uncertainty can be identified. One is what we call the parametric uncertainty, that we define the parameters and we're pretty sure about their limits, what window they will be variating in, and what we call aleatoric uncertainty that's associated with the white noise sequence. So the question that arises here is, how can we address the aleatoric variability coming from the different white noises for an X-specific parameterization? So in earthquake engineering, this is done by assuming a log normal distribution that when we approximate its statistics in its case by having the first order and second order statistic. This distribution, though, depends on the parameters X. So in the context of seismic risk assessment, we actually have to run multiple nonlinear response history analyses in order to be able to effectively investigate the parametric uncertainty in conjunction with the white noise aleatoric uncertainty. So as you may imagine, there is a double combination that needs to be accommodated, that if we have to go through the high fidelity, computationally expensive model, the finite element model that we have at hand, it will have an enormous computational burden just to investigate one single structure. So one way to reduce this computational burden is actually to use surrogate models. And surrogate models, as I already mentioned, are offering just a mathematical approximation to the problem that we have with respect to the input parameters that we have identified and the output that's of interest. So the challenge, though, here is that the aleatoric uncertainty cannot be included as a part of the input in our descriptions, simply because it's high dimensional and would decrease the complexity of the surrogate model that we need to use. So in past studies, what was done is actually to approximate the statistics of the underlying distribution. That was also very it was very, very actually expensive, simply because we had to estimate, in order to estimate accurate these statistics, we had to spend a very large upfront cost just to train our surrogate model with reliable statistics for that log normal distribution. So here we're going to take a different route, and we're going to approximate directly the EDP distribution and not its statistics as it was done in the past. And I will give you now a brief overview of the kriging, which will be our main surrogate modeling technique. And we're also going to discuss a little bit about stochastic kriging and how it falls into our solution. So kriging, it actually approximates the true response of a function as a realization of a Gaussian process, along with a linear underlying regression trend. So in fact, it has two fundamental building blocks. The one is the basis vector, which is typically a lower order polynomial that tries to detrend. And then you have the correlation functions, which is associated with the GP. And you have a variety of correlation functions that you can use depending on your problem. And this is where the bigger computational challenge arises for those types of approximation. And that's associated for the GPs, especially with inverting this correlation matrix, which is directly related to the dimensionality of your input. So what it offers when you train your surrogate model based on a data set that's available, you get back pretty much an estimation of your predictive mean and your predictive variance for a new point that has never been seen before. And just to illustrate this in a very simple one-dimensional example. So if you have your exact function and you have some simulation experiments, that these comprise your initial training database, what kriging is doing is offering you a predictive mean based strictly on those red dots without taking into account the exact function, because remember, the exact function in many cases is not well described, so we cannot plot it as I have it over here. So it offers a predictive mean, and it's a pure interpolator to some extent, but it additionally offers what we call the predictive variance. So it gives you a window of uncertainty of how good your prediction is when it comes to that predictive mean. And based on that variance that you see over here, you can add more experiments and kind of taper down that uncertainty in certain locations. So how does kriging fall into the problem that we are trying to address with the aleatoric variability? Is that we can treat that white noise influence as noise in our observations. So instead of having reliable, exact observations, we assume that that noise is causing those observations to fluctuate a little bit. So what kriging is offering an additional parameter that's called the nugget that pretty much can accommodate noisy observations. And the first approach that we're going to take into this is assuming that the nugget is constant. That means that we have a homoscedastic assumption for the noise across our point observation. And if we start from a database with n training points that map the input and output, that they are uniquely pairs, we can have the Gaussian predictive mean and variance. I'm not gonna stress the math around it. The two things that I would like to stress is the fact that the predictive variance, in fact, has two parts that describe the variability of the noise in our observations and also the variability with respect to the mean trend. And the second one is associated to how we are actually calibrating the surrogate model, and how we are training that model is by going through an optimization process. Here we've chosen the maximum likelihood estimate for that optimization, but instead of going directly for the variability of the nugget, we are having a scaled version by the process variance. What this is aligned for a decoupling in the optimization that helps it become more efficient, so you can train much more efficient your surrogate model and much more faster. So now, having established the kriging Gaussian predictions under the homoscedastic noise assumption that I already described, and knowing the form of the EDP distribution, we said that for earthquake engineering, a log normal is assumed. So we can set actually y to be equal to the log normal of the EDP of interest. So getting that way directly through kriging the approximation of the distribution that we are interested in. So, and just to give you a very, very small application, when we are dealing with a single degree of freedom, which is a one-dimensional example, here we have as our input the moment magnitude. So how large is an earthquake? You have a 7 magnitude, you have a 5.5, and looking at two different outputs, two different quantities of interest, the peak displacement and the peak absolute acceleration, we can see in the results that actually when we're trying to approximate the median, which is our solid line, pretty much our homoscedastic assumption about the noise is doing really well. But if we focus a little bit more on larger moment magnitudes and on the peak acceleration, we can see that actually we cannot describe that well the variability. So it turns out that maybe that homoscedastic assumption is not quite a good one for the problem that we are trying to solve. So we will reevaluate this by actually thinking about including a heteroscedastic error assumption. That means that we will allow for our error to vary across our input domain and not have that constant assumption that we made earlier. So how are we going to do that? Based on the training points that we have, we will now start incorporating what we call replications. So the replications will allow for us for a fixed number of X parameterization to vary the white noise. And this is something that has been done in the past. It's called stochastic kriging. But the innovation here is that we're going to do this only for a small number of replications. So we want to allow for each data point to get a very large amount of replications. And we're also going to do that only for part of the database. So we won't require for every point in our database to have replications. And just to describe the framework for you, we're going to start with a training set that has endpoints. Some of them will have replications, and some of them we're going to call them unique points. So they will be without replications in our database. For those points that we actually have the replications, we're able to calculate statistics and use those statistics to create a secondary surrogate model that will be dedicated on capturing the heteroscedastic variability. So what that model will offer is only predictions of how that heteroscedastic variability is evolving in space. So final step will be for us to join all the efforts to the primary surrogate model. So the primary surrogate model will be the one that will be formed by all the points in our data set, from the statistics that we gain from the replications, and also from the secondary surrogate model, offering these estimates for that heteroscedastic variability, with pretty much ultimate goal to get out the distribution of the engineering demand parameters. And I will briefly touch on how that primary surrogate model is being developed. Again, there is too much math. I'm not going to go through all of them. I would like just to point out some things that are crucial on the developments themselves. So if you focus on the benefit here on top, pretty much the estimation that you get from the secondary surrogate model is reweighted when it goes into the primary surrogate model for the training that you have to do. And again, we scale the nugget by the process variance, so we can have the same benefit that we used to have for the homoscedastic case. Again, for the tuning and training of the surrogate model, we use the calibration. As you can see here, we use the maximum VMLE estimate, the maximum likelihood estimate. Let's apply then this framework now that we have established, now moving away from the homoscedastic to the heteroscedastic one. And this is where we started off, and we started questioning this pretty much discrepancy that we were looking at, especially on the variability itself. And if we apply the new framework that's related to the heteroscedasticity, you can see that for the training points that are available, we have a better fit, both for the median and the variance, the variability. And as you can see, there are observations that actually are unique, so they're being repeated only once. And you have also observations that they're being repeated more times. And as you can see, pretty much with that repetition, you're able to capture better the median behavior, and pretty much the unique observations are coming and informing that variability that you are able to see. So I'm going to switch now to a much more complex example. And in this case, we're going to see a moment resisting frame. So this is a real structure made out of concrete that's modeled in a software that's called OpenSeas. We heavily use that for research purposes because it's quite flexible, and you can have a bunch of material laws and mess around with damping. So this is one that we kind of prefer using in such situations. And the first ground motion model that we're going to see is a point source model. So it will be a very, very simplistic model that will require only information about the rupture distance and the moment magnitude. And the problem formulation, just to put it into the context of the Kriging surrogate modeling that we're discussing, it will have input parameters that are associated with the material uncertainties, or with the structural damping, and with the excitation itself. So moment magnitude and rupture distance will be the ones that we're going to consider as our input parameters, kind of defining our ground motion model. When it comes to the output parameters, we're going to examine both peak interstory drifts and peak absolute accelerations for all floors. And in order to build our reference case, we will have to spend a little bit of computational burden. This is done as a demonstration, so that's necessary when you try to compare a newly established method. So we will have 1,000 X parameterizations that we have obtained through Latin hypercube sampling. And for each one of them, we are going to have 200 white noise replications. So securing that we have a large amount of replications that will actually lead us to a good average, a safe average estimation. And that will create our reference distribution, engineering demand parameter distribution. So for the stochastic rigging that we built, there are a bunch actually of parameters that might be of interest in terms of what we should examine and look through. In this case, what we are interested in is, for example, how many simulations we should be asking from the high fidelity model. And as you may imagine, the larger that number becomes, the higher is the cost that you have to pay. Why? Because the more high fidelity numerical simulations you have to do, the more computational time you have, but at the same time, your surrogate model will become much, much more accurate because it gains more and more information. So there is a competing interest of where it could be a good balance between the two. The other interesting aspect that we want to investigate is actually the number of points in that database that I described, the initial one, that will be divided between those that will actually have the replications and those that will be unique points. And the last, but actually the most important one is how many replications for that part of the database do we require to be accurate enough? So how many times do I have to go through the same X parameterization, just varying the white noise? And what we will have out of that investigation is pretty much, again, another distribution, but just for the safety of sampling those training points, we will repeat this 15 times. So that what that will give you, it will give you kind of an independence of your, the initial training points that you're selecting. So someone cannot come and argue that you had favorable training points that kind of led to the results that you can see. So that gives an extra safety level in terms of how your model performs across different sampling datasets. Okay, so what we have, pretty much we have a reference distribution, and then we have the one that's being given as an approximation from our kriging from a surrogate model. So one way that we can compare distributions is, many of you might be aware of, is the Kullback-Leibler divergence metric, which pretty much compares how close two distributions are to one another. And here you can see some results of this investigation. Here, box plots are presented, pretty much showing the variability across the 15 repetitions that I mentioned, looking at the average KL divergence across all floors for both the drifts and the absolute accelerations. So here we don't distinguish between them, we just saw an aggregated result. So each subplot corresponds to a different computational budget. We've pre-selected 3 different computational budgets, and different database formations are examined for the points with and without replications for a given computational budget. So within the same row, you can see that we are investigating a bunch of different allocations of points with and without replications. And we're also looking at different number of replications per training point by going with a smaller one to the larger one of having 20 replications on that training point. So as you can see, overall, we have a very good approximation of the reference distributions, since our KL divergence is actually close to 0 for all the different cases that we've investigated. And that's a first good indication. Additionally to this, we have a great computational efficiency in this case, because we're only spending at most 3,500 numerical simulation calls, when the methodology that I said earlier that was out there approximating statistics of the distribution would require much more than that to provide safely accurate log normal statistics. When it comes to the selection of the initial training points, and that pertains to the variability that you see within the box plot, we can safely say that the selection of the initial points, it does not appear to be that significant, and you shouldn't probably spend effort on identifying an optimal scheme on how you're going to place those training data, those dataset points for your training set. So larger, as expected, total computational cost is yielding higher accuracy results. Why? Because as I described, the larger your data set, the more accurate, data-driven approach becomes. So the more data you feed it, the more accurate that process will become. So when it comes though to the replications per training point, what we see is actually interesting. So in fact, the case that appears to be the most favorable one is the one that allocates the smaller number of replications per training point. Why? Because this pretty much allows for you to explore better your parameterization when it comes to X, so the parametric uncertainties that you have, and then complement those parametric uncertainties with a little bit of an investigation when it comes to the white noise variability. And finally, what I should point out is that for what we call a pathogenic case, so in these cases, pretty much you have 0 unique points. So for all your replications, for all your data points, you have replications. You can see that pretty much you're getting an ill-posed solution. Why? Because the primary surrogate model.
I think it's all fresh in our mind. We should really start to design that survey as soon as we can.
Sorry, I think
we have a lot of good brainstorming here from today too.
I think someone is. Yeah, I'm not sure who was. Okay, I got it. Okay, great. So going back to the non-unique number of replications. So pretty much what you have here, you have replications for every point in your data set, something that causes your surrogate model to believe that there is almost 0 aleatoric variability. Because you don't have those unique points to kind of blow up your variability for the model to see that and understand that there is more variability. You just get very aligned points that they are averaged out due to those replications. And finally, if we use the already trained surrogate model for the seismic risk assessment over structure, which was the ultimate goal. So what we're trying to do here is we vary the excitations, and we pretty much see how the drifts or the peak interstory drifts or the peak absolute accelerations as they increase, what's the probability of exceeding a certain threshold. So performing this seismic assessment, risk assessment, we can see that all the models perform well. We can see that pretty much the one that has the larger computational burden is the one that's being more accurate and there are less discrepancies, while the one that's very, very poor in terms of how the computational budget, it starts having challenges. And even for the non-recommended case that we said, where we have 0 unique points, you can see that the model is actually performing relatively okay. Bear in mind, this is a log normal scale, so differences are larger than what they might appear in the log normal regime. Okay, so we have seen so far how we have addressed the aleatoric uncertainty, but let's take a step actually back and maybe redefine what that aleatoric uncertainty might be. So let's examine what sources of uncertainty we have in this problem. And maybe now that we have established a framework that can actually address aleatoric uncertainty, maybe some of the parameters that right now we have them as parametric uncertainty can be actually shifted to the aleatoric side. For that reason, I'm going to explain briefly what the seismic hazard description entails. So you have the high-dimensional stochastic sequence, the white noise that we discussed already. We have the seismicity characteristics that represent the regional hazard. These were already there. These were the features that the ground motion model required, and they are associated with earthquake parameters like moment magnitude, the rupture distance. And then you might have additionally what we call ground motion model parameters. So out there is a variety of ground motion models that actually have a different number of parameters that describe them. And there are the ones that might have only 2 or 3. There are those that have 6, and there are those that might have 18. So you end up having a bunch of parameters to investigate that start accumulating in your input, in your X input. Why that becomes a challenge? It becomes a challenge that because the larger that input becomes, then the harder it is for you to invert that correlation matrix. And then which means that then you need more training points to cover also your region efficiently. So here, we also have in the parametric side what we were describing as structural, material, and modeling parameters. And so far, what I described, it was pretty much the aleatoric uncertainty being only the stochastic sequence and the parametric uncertainty being only on the model parameters and on the regional hazard itself. So what we're going to do is we'll try to investigate a bunch of variants where we shift some of those parameters that are associated with the regional hazard and the ground motion model description to the aleatoric side. So the goal is to investigate, and this is kind of also a sensitivity analysis to some extent, how many of these parameters can be swept under the carpet and become part of that aleatoric uncertainty that now we are able to capture fairly well, rather than having them as an additional input parameter that we need to examine. And I will give you directly some results just to convince you that playing around with them and having also the engineering intuition of how these actually work can offer you much, much more informed surrogate models that are also very, very simplistic when it comes to their description. So here we're looking at the ground motion model that has 6 parameters. And you can see for the variant V1 is pretty much the variant that I already showcased for you, where only the stochastic sequence is part of that uncertainty, the aleatoric uncertainty. For the variant V2, we actually include all the ground motion parameters, and you can see the results here. And for variant V3, we throw some of those ground motion model parameters to the aleatoric uncertainty part. What I should stress out is that variant V2 becomes very challenging when your ground motion model parameters are becoming larger. Why? Because they're becoming more influential. And if you throw all of them into the uncertain side, chances are that you won't be able, as you can see on the panel up here on the left, you won't be able to capture faithfully the discrepancy between how your surrogate model performs and how your reference case is doing. Where it becomes interesting and actually has some value is when the parameters grow larger, but we focus on variant 3. So what we do, we pretty much pick and choose which ground motion model parameters can be part of the aleatoric uncertainty, and they are removed from the parametric one. And as you can see, you can get a fairly good estimate for variant V3 if you're willing to spend some computational budget. The more you're constraining your computational budget, the more you deviate pretty much from your reference case. With that, I'm going to come to my conclusions. I think I was fairly fast on presenting this. So what I demonstrated here, and we can think that on the broader context of a system that has uncertainties when it comes to the input description, and those uncertainties are being manifested at the end and change the response that you will see in the back. So that response then needs to be mapped not to a certain value, but maybe to a distribution. So you have a response distribution that you're trying to map. And the way we approach this problem here is by developing a surrogate model that will be much more computationally cheap for us to deploy and examine a bunch of different cases that will be able to address that aleatoric uncertainty. And for us, that was being manifested through the white noise. So we started by the simple assumption that was saying, okay, what if we have a constant homoscedastic error? We proved that this is an assumption, but it's not as good as it can be. We moved to a heteroscedastic assumption where now the variability changes depending on the input. We demonstrated there that we can get better results using a toy example. And then we moved on to something that would be much more elaborate, which is a real structure, a real moment-resisting frame, where we had a bunch of parameters, input parameters, that they were informing that model. And we proved there that, again, the seismic risk assessment is much more efficient than actually executing that numerical code faithfully for the number of times that you want. We took it actually then a step further, and now that we had that framework established and we were able to address the aleatoric uncertainty, we questioned what could that aleatoric uncertainty be. And actually we tried to include not only the white noise sequence, but a bunch of other parameters that could be described abstractly in that aleatoric uncertainty. And we proved that for some cases, if you are able to spend some computational budget, you can actually do that. And with that, I think at 40 minutes, I'll thank you, and I would love to take any questions and have a discussion.
Thank you, Katrina, for your presentation. That was a really interesting presentation. And so before we move on to the Q&A session, I would like to remind everyone to please use the sign-in sheet provided in the meeting chat so that we have a list of all the attendees for these webinars, and it would help us a lot for our further webinars. So with that, I open for any questions. We have some professors with us, Professor Harvey or Professor Pai or Professor Naidu, if anyone of you have any questions. Dr. Naidu, do you have any questions? You are muted.
Yeah, nothing in particular.
Yeah.
Yeah, thank you.
Okay. We have a comment from Professor Harvey.
Yeah, let me put forward what Katrina has put together. I think this is a superb example of not just using surrogate models as in the past, where we did that to reduce computational complexity. What he's brought into this picture is how it can be used in terms of solving a problem that has many steps to it and many phases to it. So I think this is a very, very interesting development that she's put forward, and it can be used in many different domains. People who are solving engineering problems and not just looking at approximating the behavior of the system exactly. So this is a step forward. And Janet and I are interested in this domain, and we've done some work in this area. So the comment for Katrina, a question for Katrina is, have you thought about using ensemble surrogates? Not just kriging and—
Yes.
Okay.
So the
ensemble surrogates, and how would you use them?
So the problem that arises if you have an ensemble of surrogates is that they have to be compatible to some extent on what you're getting out of them. So in that case, because I'm assuming, if I'm not wrong, that when what you mean by ensemble surrogates is combining different surrogate models to get your estimations and maybe weight them or have a different way of merging them. Am I right?
Yes.
That's the definition. Okay, yes. So the problem that lies there is that you need them to be compatible to some extent in two main ways. One is that they have to have a very similar computational burden. And what I mean from that is that if you try, for example, to go to neural networks, you'll need a much, much bigger database if you want to deploy a neural network and map out all the parameters that you might have. And you also need for them to be giving you the same level of information. So GPs, for example, give you also the variability, and here we leverage that variability to some extent to guide our problem. So you need compatible surrogate modeling techniques that will offer you that variability, hopefully without any extra computational burden. That's one of the things that, for example, neural networks cannot do well. PCs, yes. So polynomial chaos maybe would be a good complementary, surrogate model in this case. But because we, in our problem definition to some extent, those numerical simulations can be quite expensive. You have to be very, very strategic about how big is your computational budget. That's one of the problems that we run into, and that's why we didn't push it to, larger than 3,500, because people would be like, why you're not doing 5,000, why you're not doing 7,000? Well, the more complex your model becomes, then you take a toll in each run you're calling that model. So I cannot come up with a very, very large training database because it doesn't come for free.
Perhaps we can take this conversation on offline.
Yeah. No, but it can be, if you can identify them, I don't see the reason why you could not use a surrogate model and sample. You just have to be very careful on how you will combine those models.
Thanks.
Sure.
Professor Jin Song,
yeah. Jin Song, go ahead.
Thank you. Thank you very much for Katarina's excellent presentation. I'm wondering about if, in the process of research, if Katarina has encountered a situation making her feel, something called conservation of difficulty. I learned this initially as a mathematical joke, but there's no joke. We're modeling something, with high complexity. So some hard work needs to be done somewhere to take care of that complexity. So I wish to hear any comment because I realize hysteresis is involved, right, in this kind of modeling. Yes. So. Yes. Yeah, and at the meantime, I don't want to take away time from other students. Thank you.
Sure. So yes, there is some inherent complexity when it comes not only to the structural parameters. You can think of any problem, right? You have parameters that are much more challenging and might also cause your response to be much more different once you vary them. And you have other parameters that might be less significant. There were challenges, especially on the model, the ground motion model that I used that had the 18 parameters. I would say that parameters that I was expecting them to be influential, some of them, they turned out not to be that influential. Because just to give you an idea, those ground motion models for the broader audience, in some cases, they might just be fitting data that's out there. And they feed data and they create distributions with respect to, I don't know, the frequency content, and, they describe those distributions with certain parameters. So that 18 model, ground motion model, had a bunch of parameters that some of them, you could throw them away from the beginning and throw them into the aleatoric and be sure that you won't ever, be bothered by them. But there were other ones that they were much more challenging and identify whether they should be included in the parametric uncertainty or in the aleatoric one. You need engineering intuition, and then you have to do some trial and error. Hysteresis is another big chapter. We, in that research, we only explored the bunch. We didn't investigate different laws. We had one law that we were investigating. We're just shifting the parameters of that law.
Thank you.
I have another comment or question or observation. Katrina, you're applying this to earthquakes, right?
Yes.
And you're approaching it from a cyber-physical perspective. Mm-hmm. There's a cyber side that deals with connectivity and computation, and the physical, which is the earthquake itself. But there is time involved in this. And in abstract, you mentioned about time dependency, if I remember right. Can you expand on how you deal with time dependency? And let me tell you why. Because two of my students, Mayank Balerao and Shyavas, are dealing with the evolution of systems from a time perspective. So if you could share some ideas or papers, that would be extremely helpful.
So I've dealt with time dependency not on earthquakes, because they don't give you enough time to map, to make that time evolution to some extent. So in earthquake engineering, what we do, we use maximums, but I've dealt with time evolution when it comes to storm surge. So it was a different problem. The time evolution plays a role. And yes, I have some ideas of where I can point you in terms of time evolution events.
I'd really appreciate that because we are looking at cyber-physical social systems and the evolution of cyber-physical social systems. So the social side comes into it. But we've got some handle on the cyber-physical social side, but the evolution side is what we are searching for, and ideas and people who have experience in that, like you, would be very beneficial to us.
I can send you some of the time series that I have worked that look on time evolution, and I think I have a colleague that I know is currently working on a project that looks at the time evolution of, I mean, it's a physical phenomenon, but still, if your social, your cyber social is kind of has all the same assumptions, you might be able to do it. So he's currently making projections of time evolution when it comes to surge responses from historical events. But he's using neural networks. So neural networks is what he's trying to use to inform that prediction / forecast.
Well, for example, just for the folks in mechanical engineering, those of you who do experiments, and those experiments take time, and you want to simulate the process of material forming and things along those lines, particularly when you're doing additive fabrication and stuff like that, what Katrina has put out here is a phenomenal model for you to look at.
Yes, and actually I wanna add that if you want to complement this, probably you know design of experiments notion, right? So design of experiments is pretty much an optimization process of how you can place those training data points into your domain. So when it comes to experiments, you want to know which experiments will yield the most informative results, right? So that way, what you can do in that optimization is you introduce a surrogate model that will fake the result just for you to judge how good that result will be. And then you proceed with the execution only if you feel that it will be beneficial to whatever you're investigating. So design of experiments is a big kind of era where you can place your experiments, physical or computer experiments, on a much more educated way. And this is where surrogate modeling plays a role, because you don't have to go and run the experiment, come back with the information. You can build a surrogate model to tell you how things will, predict how things will go.
Katrina, I'm going beyond that. These fellows in mechanical engineering, they deal with material flow, casting, composite materials, polymer materials, stuff like that. And so time is involved in that because there is a flow that goes with it. And so the work that you have shown right now and that you'll be sending us on storms and other aspects fits into what they're talking about. It's not just to reduce computational complexity or time to do experiments. What you have put forward here is a way to look at flow. And that's what I'm suggesting to our folks in Jivtesh, Garut's laboratory, and others who are involved in additive fabrication could look at.
Yeah, I'll make sure I'll send you these. I'll contact also the person just to see whether I can access their article. Sometimes it's hard.
Right. Something back to you. I've done my bit.
Yeah, thank you. So is there anyone who has questions for Katrina? Anyone from the students?
Right.
Okay. Farooq, do you have any closing statements?
Yes, Katrina, this was a fascinating talk that you've given. Very comprehensive, very nicely done. And conceptually, I think there's great opportunities to take this further as to what you've done, making it to an engine that is not just for earthquakes, but that can be applied to other domains as well. And it was very well explained and very well put together. So, and you got me thinking about other areas in which this could be used. So I've had a great time listening to you. You've polished my mind, and it feels very nice to have you here. And you've drawn a very good audience, which is testimony to the topic that you put forward, and also the interest that people have from not just mechanical engineering, but there are a number of people from civil engineering, and there are people from computer science who are out here. So the lady from computer science who's doing her master's, there is an opportunity here for you to look at how to save time in doing experiments and working something out along those lines, particularly using machine learning and things along those lines. So there's a great opportunity here, a wealth of master's projects and PhD projects in what Katrina put forward. So thank you very much. And thank you, Swapnil. And I'm going to, in our usual way, I'm going to stop the recording. And what we do is, when the recording stops, it's a time for chit chat.